Hello everyone. In this video, I will talk about Maxwell's third equation, also known as Faraday's law of induction. If you haven't watched my previous videos, but where I talked about Maxwell's first and second equation, I will highly recommend you to do that. In that case, you would get better understanding of Maxwell's third and fourth equations. So before going to the equation itself, I typically first describe things in as a visual representation, or like in a bring a life example, and then move to the equation and connect it to. So in that case, we have better grasp the concept of the equation itself. All right, let's go ahead and get started. Imagine you have a ring, just a normal metal ring. And then you have a magnetic bar. So it's just a normal bar, magnet bar. And you know from the physics it has a north pole and then south pole. So what happens is when you move the magnet's north pole into the ring, when you do that, when you approach it like to the ring and then you get it inside the ring, the magnetic flux through the ring increases. So let's draw it more carefully. Here is the ring, and then now you have this magnetic bar just now inside this ring. So what happens is this magnetic bar, it has this own magnetic field. If you see my previous video about the Maxwell's second equation, it has this magnetic field that's going from north pole to the south pole. So this magnetic field, and that magnetic field, it increased the magnetic flux throughout the ring, and the change in the flux actually induces an electric field around the ring. So we have this ring. Now that ring has this now electric field. The magnet induced the electric field. Let's draw the electric field around this the magnet. So I will just draw it like that. So now it has this induced electric field that's due to this magnet. So now what happens is that electric field pushes electron, and that creates a current in a specific direction. Let's say in our case the clockwise. So now it has a direction, so it's moving to the one direction. So I'll just write it as an arrow. So we have here arrow clockwise, so clockwise. So now we have an arrow which is the direction of the current electric field as a result of the change in the magnetic flux. So now what happens when we take the magnet out of this ring? So now we have a the ring, and then the magnetic bar is now, I'll just draw it a little bit far from here. So now what happens when we take it out, take it away, again it induced the electric field, but now the direction of the electric field or the current, it flips. So here it goes, if it goes the clockwise, and here now it goes the counterclockwise. So now the arrows are on the counterclockwise. Oops, apologize. So let me just rewrite this. Now it is counterclockwise. So think of a magnetic field as a pushing through the ring. If the amount of magnetic field increases over time, the nature responds by creating the electric field that goes around this specific ring. So this electric field can drive the charge around the wiring, and that's how typically the generators work actually. So in summary, moving the magnet into or out of the ring, the magnetic fields through the ring it changes, and that change is going to create the electric field, is going to induce the electric field, and that electric field will drive the current in a specific direction. So the key word here, the change in magnetic field, is going to induce the electric field. So that goes in a specific direction. So now let's write the equation itself. All right, so here I wrote it down, the equation, the Maxwell's equation. So let's go from left to right. I'm just gonna change the color of my pen. All right, so as you know, this part means the integral. So you've already seen integral from your calculus class, and this little circle here, that means it's a closed integral, just like you see on the loop. It's closed. If it would be open, then there wouldn't be a flow of current. So that's why we have this little circle, which means the closed integral. This E represents the electric field. In the arrow, of course, it's the vector field, has this direction, which I mentioned here, the field of the electric direction, the direction of the electric field. And this dl here, it's very important. So dl is the tiny segment over which electric field is measured, the tiny segment of this loop. So now here, if you remember in our Gauss's law, there was a dA. In Faraday's law, we're not enclosing the volume like we did in Gauss's law. It's not dA, but it's dl. So we're focusing on a closed loop. It's like a ring or wire, and that's what's happening around it. So that's why we use this dl, a very small line segments around the loop. So what does this term here represent? So this whole term measures how quickly the magnetic field through the wire through this loop is changing over time. So that specific term in numerator, it's the magnetic flux or total magnetic field, and we have also dt, just time. So basically it measures how quickly the magnetic field through the loop is changing over time. So, and there is one small thing that you need to pay attention, it's this negative sign. So it's very important to understand why we have this negative sign here, and this specific sign is explained by a different law. We call it Lenz's law. So let's quickly go through it. It's not that complicated, but if you want to learn Faraday's law, you need to know what Lenz's law is. All right, so let's talk about Lenz's law now. Excuse me. So just to recap the Faraday's law, again, when we start moving the bar magnet towards the loop, the magnetic flux they begin to change, and that change flux is what triggers the response. And according to Faraday's law, the changing magnetic field is going to induce the electric field around this wire, and that electric field is going to drive the current loop either clockwise or counterclockwise. So now there is one thing that needs to be taken into account is the local magnetic field. So let's drive our draw our the loop. So what happens is the around the loop there is a electric field, and that's of course after we bring the magnet there. So I'm just gonna draw the magnet again. Okay, so that's due to this the induction, like field induction. So and that current, because we have a current here now, which is going the electric field current, which is going in our case the clockwise, and that actually generates the another immediately generates the magnetic field around the loop. So see, now we have a different type of magnetic field, and that magnetic field is called also local magnetic field. So it's a local magnetic field. Why? Because we have another type of magnetic field also. It's due to this magnet bar that we have. So this magnet bar is also has its own magnetic field, and if you watch my previous video where I'm talking about Maxwell's second equation or Gauss's law for magnetism, I'm explaining there how the magnets behave, the magnetic field. So we have here magnetic field, and we also have this local magnetic field. So what does Lenz's law says this, and this new field always acts to oppose the change that caused the previous magnetic field, that caused it. So this local magnetic field always will be opposite. It's, you can see, as direction is opposite as this the main magnetic field. So that's what Lenz's law is trying to say. So basically, when we have a loop, when we try to bring the magnet, so, and you can do it by experiment also, when you do that, you will see a slightly a push as you take the magnet inside the loop. You feel a little bit push force, and that's what is was done, is generated by this local magnetic field that was generated by the current. Okay, so when you try to pull the magnet bar away from this loop, what happens is you try to push, so if you feel a little bit a pull force, and that's also generated by this local magnetic field. So they're always kind of opposite to each other, and that's what Lenz's law is talking about. So in general, Faraday's law, it basically quantifies the magnitude of the induced electric field. So that's why you see the electric field here, which is proportional to the magnetic flux. So that's what generated by the Faraday's law. And on the other hand, the Lenz's law actually determines its direction. So the direction of the magnetic field.